Hello everyone. Today I'll talk about a static code analysis tool called Rapid, which checks API usages in code for the cloud and in the cloud. This is work done with my colleagues at Amazon Web Services.
Modern software applications use a multitude of cloud services hosted in the cloud. These services are exposed to the client via APIs. For example, NoSQL databases such as DynamoDB provide key value stores. Amazon S3 provides storage. Amazon KMS helps a customer manage their cryptographic keys. AWS Lambda provides compute for serverless computing. One common aspect of these APIs, which are exposed in the code via SDKs, is that they're RESTful. The requests and responses associated with RESTful APIs are short-lived and local. To securely and efficiently handle data in the applications, developers also use general-purpose Java APIs such as Java Cryptographic APIs, Java Stream APIs, APIs for XML processing, and so on and so forth. One commonality of these general-purpose APIs with RESTful APIs for cloud services is the local and short-lived nature of the objects created by these APIs. For example, it is considered best practice to not carry references to sensitive objects like an instance of JavaX crypto.keyGenerator in the Java heap memory. Let's look at an example of an application interacting with DynamoDB. A batch request is made using a DDB client. The user checks if the responses are empty. Unexpectedly, that's not enough. There's a potential bug here that can result in incorrect or incomplete results being returned to the customers of this client. DDB tables have limited throughput and may return unprocessed items due to throttling. The user needs to check the unprocessed items in their code. The user is also asked to implement a retry mechanism with exponential backoff to mitigate the effect of throttling. As you can see, the API usage is described informally at most, mainly in documentation. It is desirable to save the developers the effort to always go through the documentation and find issues with their API usages as early as possible, well before deployment, example, during code reviews. To address this issue, we want to build an industrial strength analysis that checks API usages. Our goal is to build an industrial strength Java API checking tool that resides in the cloud. We want the tool to provide feedback to the developers automatically without them adding annotations to the code. The goal is to integrate with continuous integration and code review systems such as GitHub and provide recommendations on user actions, example pull requests. The tool needs to be fast, that is, provide fast feedback in the order of 5 to 10 minutes, and scale to large code bases. Here is an example of how we want to provide feedback on code in GitHub. Our key insight is that the objects associated with RESTful APIs don't require tracking deep heap references in code as compared to stateful APIs. Let's look at how we leverage this insight to build the analysis. The key insight of the analysis design is based on the properties of RESTful APIs. The objects associated with these APIs are short-lived and are not written to the heap as per the best practices. The correct usage typically involves configuring the request with parameter values from a whitelisted set of literals. This idiom allows us to avoid a complex value flow analysis for tracking constants. Example, avoid modeling string operations. Thus, we can implement a fast and automatic analysis if we restrict the analysis to RESTful and other stateless APIs. This motivates our design choice. We want to check properties on subprograms that use APIs with these properties. We build a type state analysis with two main components: a forward local field insensitive and lightweight analysis tracking these short-lived objects, and a backward global reaching definitions analysis that can be invoked on demand by the forward analysis. The local analysis tracks aliases locally and avoids expensive whole program alias or pointer analysis. The analysis is built on top of Suite and IFDS IDE, a framework for whole program analysis. Let's look at an example property. The developer is trying to generate a cryptographic key using the Amazon KMS service, specifically using the Generate Data Key Request API. The property we want to check here is that while building the request object, the key spec needs to be in a whitelisted set, and either key spec or number of bytes must be specified, but not both. Rapid uses a finite state machine representation of a property with states and transitions. The property is defined using a guarded finite state machine language where the guards are predicates defined over bytecode. An example is the isArgumentInSet predicate, which checks if with keyspec method is called on the tracked object instance, and if the first argument to the method is in the set of accepted or whitelisted literals, here AES 128. The object allocation instantiates an automaton. Then the instance moves to the onSet state when one of keyspec or number of bytes is set, and moves to the error state when both are set. The properties and predicates are implemented via a plugin architecture, as they can be added or removed from the core analysis. Any predicate can invoke its on-demand sub-analysis. For example, at the init state, to evaluate the two guards using the predicate isArgumentInSet, Rapid needs to know the values of the reaching constants to pvar. The first argument to the with keyspec method. Rapid needs to know what are the values reaching pvar from other parts of the program, as pvar may be defined in other classes or packages in classes fields. To resolve pvar, Rapid invokes an on-demand backward analysis from pvar. The global on-demand backward analysis computes these reaching constants in a field-sensitive manner to resolve the predicates. Let's look at how Rapid works in practice.
Rapid is deployed Amazon-wide as part of Amazon's code review system. Based on metrics over a period of 4 weeks collected during evaluation, Rapid has an acceptance rate of 76%. 57% of the properties had 100% acceptance rate. Median latency on systematically selected repositories from a set of 26,000 Maven repositories is 239 seconds, meeting our low latency requirement. Although Rapid may not meet the low latency requirement for customer imports with arbitrary size and number of seeds. To address this issue, Rapid partitions the input repository ahead of time with partitions of classes using a greedy bin packing strategy. Check out the paper to find more about this trick to scale to large code bases. A fixed partition size of 1000 yields a 85% reduction in latency with only a 2% loss in findings for Rapid's checks, which are largely local in nature.
Rapid has been launched as part of an externally available service called Amazon CodeGuru. CodeGuru is integrated with GitHub, and you can scan any Git repo if you onboard with CodeGuru. Example on a pull request, on a Git push, or you can run an entire repository scan. Try scanning your favorite Git repo with CodeGuru Reviewer today. In the interest of time, I'll not discuss several other interesting details in the paper, such as details of the guarded state machine language, composing these finite state machines or automata specifications into groups based on dependencies for efficiency, reducing automata size while expressing different permutations of API calls using key value stores as part of the analysis domain, Rapid's precision and recall on OWASP, an industry standard for security checks, and Rapid's performance breakdown,